Okay, I think we're ready. Great. Week number 4. Yes. I was traveling last week and Paul gave the lectures and I will do a quick recap of week 3. I know there were some questions, so I will do my best to follow up on them. Also, I want to emphasize that we receive all the pre-proposals. Thank you very much. I'm really excited already with all these projects. And we are starting the process of the project in the sense that we'll use the next 4 weeks to refine your research ideas. So the next 3 research project assignments are designed to help you with this process. And also, we assign for each of your team a primary TA. They should all have contacted you or will contact really soon, probably today, to set up a meeting, hopefully this week, if possible, and then like tomorrow or Thursday, if you are available. The idea is to discuss with them your research ideas and also any questions you have. They are your primary TAs. Each TA has 4 to 5 teams, and so they're really dedicated to each team to help you. There will be in Piazza a group created for each team, and a little bit secret, each team has a number, and it turned out the number was just assigned by how quickly you submitted your pre-proposal. So there's no scientific ordering there, but we use it internally. So if you're called team 1 or team 20, this is all based just on that numbering. It helps us to identify the teams internally for that. So the first project assignment, which was posted yesterday, so there's no reading assignment this week, and it's by design so that you spend this time on the project assignment. And this is step number 1 of any good research. Is like you have this initial idea of like, oh, this is an interesting problem to look at. You have some possible ideas, but before you go too far in that, read the literature. What are the other ideas that are relevant to that? Now, some of you pick data sets that have already 20 papers on. So in a sense, literature review will be easier. The harder side is if you already have 20 papers on the data sets, is the research ideas that will be a little bit more challenging because then many ideas have been tried for that. So that's a trade-off, and it's not because you suggested in the pre-proposal 1 data set that this has to be the one for the rest of the semester. You have about 2 or 3 weeks to make a change. I will say in 3 weeks from now, we'll get a little bit late to start that, but it's not too late at this earlier stage. So the goal of this is we are starting to write a paper. At the end of the semester, you will have this ICML, which is a machine learning conference, ICML paper, I could say ready to submit, with some usually extra, but the idea is to use the same format. So the format for submission is the same as ICML conferences. And the first step of any paper is an introduction. No, maybe not all of you have written research papers. So for the first assignment, we will be lenient on the introduction and try to give you as much feedback as possible. We will be a lot more careful about the related work because there's expectation of how many papers. It's about, I think, 12 to 15. Experimental setup should be just a way of rewriting what you wrote in the pre-proposal about which data set you plan to use. And there, the research ideas is your first attempt about the new things you would like to try. And one thing I want to remind you, your grade has nothing to do with your improvement over state of the art. So even if your approach does not improve over state of the art, this is not the issue. As long as you know why it did not work, that's really the interesting thing, because research is a bunch of failure. Eventually you have a success. So maybe 1 out of 5 teams will get a successful ideas, or 1 out of 5 ideas, I should say, not 5 teams, 1 of 5 idea, out of 4 ideas. So the approach we have is as many research ideas as you have teammates. That's a good way to start. You have all these ideas. That also, for us, allow us to enable this very large class of 100-something students, because now you all have an ideas you can push, but you are working together in getting the data processed, maybe implementing the baselines, and maybe some of ideas will be done through 2 or 3 or maybe all teammates. But the reality is you cannot have 5 teammates working on one research idea. That doesn't work as well. So that's why we allow research ideas as many as number of teammates. And at this stage, you probably all want to meet either with me or Paul to discuss your research ideas. And I'm looking forward to meet with all teams. But to do that, it's much more efficient for me to see a first draft of your research ideas. So your deadline is on Sunday. What is my Monday plan? Monday, I'm reading all of your proposals, all your research ideas, taking notes of it, so that I will have meetings later in the week for the teams. And Paul is also doing a subset of the teams like this. So the idea is that you will get this very hands-on feedback. But instead of having you explain to me the idea during the meeting, I have a nice write-up of it. So as much as I can after this lecture and Thursday's lecture discuss, but I will much prefer that you do the first draft, talk with your TAs also about it, or primary TA, and get a first draft there. There is no bad ideas, but the place where I may remove points for the research idea is clarity. Like if I read it and I cannot understand the idea, then there's something to be improved. But the fact that the idea is a little bit incremental or way too adventurous, like that should not stop you at this stage. As we go along, I will say, hey, this is a great idea if you had 2 years, because you will need to create new data set to evaluate. So why don't we scale down a little bit the idea? And sometimes I will say, hey, this is a great idea, but it will be 3 lines of code in Python. Why don't we try to do a little bit more for this class? So over the years, I am a good judge of these bots, and I will go both ways. I don't want you to do something that you can't reach in the semester, but also my job as an advisor is to push you a little bit more to try something different. That's not just the typical, I'm taking a bunch of feature, put it early fusion. So I want you to. So today, the 2 main sections is related work and research ideas. And related work should also give you ideas about what to try. And also will give you ideas on what your baseline should be. So that's the first assignment. I'm giving you a first glimpse. The 2 next assignments are also designed to help you with the research idea. The second one is one of my favorites. It's one of the hardest for students because they don't used to do that. But it's the data set where you look at your data before doing machine learning. You will look at the data. I even suggest sometimes I call it a simulated AI. What's a simulated AI? It's a student in a box. Okay, and there you are yourself looking at the data and trying the task you're about to ask AI to solve. And as a human can get an intuition of what's hard and easy. There's other exercises like this that we suggest, like for example, looking just unimodal baseline and see how well maybe language is performing so well on these examples, but failing on these other ones. Like that will also give you an idea of where. So that's the second assignment. And the third one is the key one. At that point, we'll add the midterm. That's called the midterm. At that point, you implement the baseline models. And at that point, you should have your final research ideas because you've tried the state of the art. And this, you see where they fail. That will help you refine your ideas. Number of teammates is number of research ideas. And for this, and that's true for every report, it will be scaled by the number of students. I don't think we have teams of 6, but teams of 3, 4, and 5. That's perfect. I think we have about 20 teams. This is exactly what we needed. That's also why the size of the course can scale, is that we'll have midterm presentation where it's really fun, because for me, I hear about all those research ideas you have. So that's the first assignment. And then next week, I will send that probably later this week, we'll meet with the instructor, with Paul and myself. These will be 15-minute meetings. I'm prepared. I've read your proposal. I read your research ideas, and we discuss it. Now, if you need follow-up discussion, we can always meet again, or we can discuss through Piazza. But these ideas will be to have most of these meetings on Wednesday and Friday. There's no lecture on the Tuesday. This is in a sense a replacement for that extra meeting that we have to make together. I personally will have probably about 6 hours of meetings with all the teams. So we're removing that lecture, but there are lectures next week on Tuesdays and Thursdays. So there's a lecture Thursday. There's 2 of them next week. The following week, there's no lecture on Tuesday. That's kind of replaced by this. And there will be a guest lecture also the following Thursday that week. I will share the Piazza sign-up sheet for this. Okay, so the lecture today is about multimodal alignment. So we've talked a lot, in fact, about multimodal representation. I will do a quick recap of that, and also address some of the early questions. I really love your questions. These bring me inside, and even sometimes from your question, I'm like, let me rethink this. And one of the questions was like asked about the connections, multimodal connection. And I want to rephrase that for you so that I can give an even better definition. But multimodal is this 3 things: heterogeneous, connected, and interacting. These are the 3 principles of multimodal. Heterogeneous, we already discussed. I just want to revisit connected and interacting. Connection, I want to give you another definition. I already gave you one, but connection is knowledge from one modality that provides information about another modality. And this in statistics is also known as association. Association between features. But in our case, we have association between modalities. What it means is, like, if I say kitchen, there is some object you expect in the image. Or if I see this image, there's certain words you expect. This is the association. There is this connection. There is this established connections between language and vision. And that association, I will use the word connections. We could call it association. We could call it dependencies. All of these are related. Association, dependencies, connections, just very similar concept. And this is the idea that often one modality is connected. One modality is, if I look at the elements of that modality, it tells me what is likely to be the element of the other modalities. And so there are different connections. And the one statistics loves the most is co-occurrence, like probabilities of co-occurrence. Probability of co-occurrence, joint probability. Okay, that's a similar concept. The idea that it's very likely that I have a kitchen and the image of an oven. This is just co-occurrence. The joint probability of kitchen and seeing an object oven is higher than maybe other object like a sofa and the word kitchen. So that joint probability, that co-occurrence is key to a lot of statistical approach and probabilistic approaches. And then a step further is it's not just that these 2 objects in itself are co-occurring, but there is some value of it, maybe their colors or some values are correlated with it. It could be correlated of the feature themselves, or you could say it's correlation of the probability. So correlation, we will see it more, most of the time I will use it is often there's a correlation, but correlation of the probability of occurrence. If I see kitchen, there's higher likelihood also of the correlation of the probability of seeing an oven. Okay, that's correlated in the sense that their probability are correlated. But there's also the word correlation is often sometimes used because the values themselves, like I have maybe an emotion value, an emotion label, and then I may have a facial action unit 12, which is smile. So smile and they are correlated, their values are, so it can be at the input or at the probability of co-occurrence that you have correlation. And there's a lot of other connection. There's causal connection where it's no more correlated, but now I have, because I've done either experimentally or through some other method, I know maybe the counterfactual, and I know that this really caused the other. And there are other relationships like this. So there's a lot of those connections. And for a subset of that, co-occurrence, primarily, people are using those Venn diagrams. And I will use them a lot, but at the same time, they have their problem because there are a lot of connections that are not visually, you cannot see that explicitly in this. But the co-occurrence, we can see that because the shared is about those like jointed probability that the events are co-occurring together, while unique are those probability, in this case, that the event is happening independent on the other elements of the other modalities. And then, so if you look at these representation of co-occurrence, then you can say something is strongly connected. Strongly connected, the extreme version would be every element like jointly appear with the other modalities, like there's a clear connection, while the extreme is completely unconnected, where if one word is spoken, I have no clue at all which object will be in the image. That would be completely unconnected. I wanted to clarify this. There was this whole discussion of statistical and semantic. This may be a little bit, it's just different type of connections. I will remove that naming convention from all future slides because of those questions, because at the end of the day, the important part are the type of connection, but the most important is the basic concept that one modality gives me information about the other, and often it's a symmetric thing. And I want to emphasize that the connections are in the data. Their connection are because I have paired data between language and vision, or I've, as a human experience, seeing object and hearing words, and I made those connections. But the data, the experience is, that's where it is. Now, the model is going to try to learn the same connection. So sometimes it gets confusing because we're like, oh, the connection are in the model. The connections are in the model because the model is trying to learn what's in the data, but the connections at the basic are in the model itself. In the data itself. The modalities have that connection. They have that connection because of co-occurrence. Now, there may be a causal connection that I will just never be able to model because experimentally it's going to be impossible for me to know the counterfactual. So there may be connections there that I will never be able to discover. That's one thing, but the data itself has that connection. It's not like the model created. I mean, the model could hallucinate connection. They're really good at this, but at the basic, the connections are in the data. I want to also emphasize that because we had questions about, is the transformer learning connection? Yes, the model is designed to learn some of these connections, but the connections are originally in the data. And so we did through example, I will go a little bit quickly over that, but we showed some example of coordinated with clip embedding, where you learn language and vision embedding in such a way that they are coordinated. And as we remember, we use some contrastive laws that makes the positive sample close to each other and bring the negative one further from each other. And what's really cool of these laws like N4 and C is that this one is in fact modeling something that's very close to mutual information. And I'm going to emphasize this because I know there was confusion about PID, which I will discuss in a second, but like mutual information and just in general information theory. So at the basic, from information theory, if you had to associate one emotion with information theory, is surprise. Okay, there's something surprising in my data. If it's something that's not surprising, I expected, or there's a flat distribution, but a peaky distribution, something unexpected, and that's why information content is often equal to 1 over p over probability. Something that's very probable will have very low information. Something that's really unlikely or improbable will have a high information, the high entropy when we aggregate over a population. So that's the first thing. Now, what we did mathematically is design this equation, and that looks maybe scary or unintuitive, but it's a simple equation. It just says, like, what the probability of the two events happening jointly, joint probability, divided of the event, this is just normalization, of the event happening by themselves, the marginals. And so a mutual information is the ratio between them, or just the distance. It could also be a KL distance. But it's every time you see mutual information, think of the numerator. This, in a sense, is the very important term. It's like, if you see the mutual information, just think, oh, joint events, that the two modalities are appearing at the same time. Another word for mutual information, co-occurrence, that they are related. So this is really about measuring. When we say shared, they're shared because they're co-occurring, because kitchen and oven co-occur. That is mutual information. Mutual information is all of those words that co-occur with an object. So that's what mutual information, and that's what CLIP is taking, is saying, hey, every time there's co-occurrence, I'm going to increase that. And when there's not co-occurrence, that they're separate, that the word tells me nothing about the objects there, then that's the negative example. So we'll discuss a little bit more today about connections and alignment. That's what the lecture today. But I wanted to also discuss modality interaction, because that's the third important building block. And that one needs a response. There's no interaction without a response. And as we discussed about it, and I want to emphasize again, it's a response because of human brain or an animal brain or some other. It could be a response because of a human, like I'm seeing those modalities and I'm inferring, or it could be a model. A model could try to learn what the human, but in a sense, again, the interaction is in the data first. Is in the data. When I have input and the response output, the data already has the interaction in it. My model is going to try to learn that interaction. Again, I want to emphasize that it comes in the data. Why? Because I have input and output. And input and output could be because I have labeled supervised data, or I made some very fancy way of doing self-supervised learning, or I'm doing translation of one modality for another. But any of them, there is a need to go from input to output. That's when the modality. So that's what I want to say is that contrary to connections that can happen just because the modality, I observe the modality. Here, it's not just the modality, but you also need the response to it. And a taxonomy that we gave you, I'm just going to restate that taxonomy in a slightly different way. There's 3 levels of interaction, 3 levels that were shown differently in the lecture, I think, last week. But at the first level, it's kind of, I could call it the black box level, is that I observe some input, I observe some output, but that's it. And I'm just trying to understand the different type of interaction just based on those input and output. And I try to see, hey, is my unimodal response very similar to my multimodal response? And that's what when we talk about redundancy. Or is my response just completely different to the unimodal responses? That's emergent. Something comes out that was in neither modalities. And what you spent Tuesday last week is the internal mechanics. Is not just response and input, but we are trying to ask ourselves, what happened in between? What were the intermediate steps to get from one to the other? Is it that we added them, multiplied? Is it polynomial? That is kind of trying to understand the internal mechanics, not just the input-output approach of it. So a taxonomy is about categorizing. So a problem will be categorized because of input and output, but also often we'll try to categorize because of what we understand of its internal mechanic. Again, it's in the data. The model are going to try to help us. And finally, it's not just 2 elements, one from each modality. Each modality has many elements. Like you have an image with many objects. You have a sentence with many words. So it's about contextualizing the interaction. You have those element-to-element interaction, but because you have many objects and many words, it's a many-to-many interaction. And we need to understand what are those core connections and how the interaction between all these elements. This is what the lecture today is about. And in fact, the next 2 lectures also are about contextualizing and aligning them. But I want to go revisit this because there was some confusion on this one. And as I mentioned, interaction happen because there's an input and an output. And so in this case, the information theory, which we talked a lot last week, is just one framework to study interaction. It's not the only framework. I want to emphasize that. Like, this is not, in fact, it really emphasizes co-occurrence again. Or you could say correlation of the probabilities. Like, what is the correlation, or in this case, the co-occurrence of it? So the previous slide, I said mutual information between 2 modalities, and the shared is the mutual information. The challenge here is I have suddenly a 3rd variable. And the reason we showed you so much math on Thursday is that 3 variable mutual information with 3 variable is undefined. It's an ongoing research topic. And that's the reason there's a lot of state-of-the-art research in multimodal, because 3-way mutual information is still an ongoing topic. And I will give a high level of it, and then we can go in more details over the semester. I want to leave time for the alignment. But now we suddenly have this variable, this output. So I have 2 inputs and I have an output. So what is this? This is the information, let's say from language. This is the information from language that is relevant to the task. By relevant in the information theory perspective and the mutual information, If I say this is about the mutual information, in fact, just for a second, let's just look at this part. Mutual information between two. What does mutual information mean? Co-occurrence, okay? Just joint probability. So mutual information, it just means that in the data, you observe that label with that word. You like happy label, and that word were just observed. That's what the mutual information is. It's normalized by, like, as we discussed, like the marginals, like the px and py, but it is at the core is really just like the fact that you discern the co-occurrence. Now, the fancy thing here is that you will say, but without the blue. Without the blue, it's just, in fact, it's implemented. Part of it is just by normalizing. You're going to divide. You're going to try to remove all the variance that's related to blue. You're going to try to remove all the information that's correlated with blue. And the way to do that mathematically, I'm not going to repeat it mathematically, I'm just going to give the intuition, is by dividing by P of blue. By dividing by P of blue, you're reducing the impact of that modality on that measure. If blue was changing for those samples, then that variation is going to be removed. So only you're looking at joint, but let's say it's a kitchen and a happy. But every time I see kitchen, I also see an oven. There's a relationship. Then kitchen will not have as much influence, because kitchen and oven are happening with happy. Maybe it's someone who really likes kitchens, okay, and that makes them happy to cook, okay. So happy was related to kitchen, so it will be useful, but it's divided by the division. And in this case, it's related to one of the elements, which is oven. So then it's not something unique anymore. Like kitchen makes the person happy, but I see also oven, so it's something shared. But maybe they also like a sofa or some other thing, bedroom or something. Or multimodal, yeah, that's what it is. They love multimodal. They love the word multimodal. They love how it sounds, and they research. So then multimodal becomes something unique to that modality that relates to happiness. Happy because you do multimodal, but may not have, for some reason, any equivalent to the other modalities. So that's what's unique. And mutual information that is conditioned on removing this impact of this, that is mathematically well defined. It's similar to the conditional entropy that we studied also lecture. So similarly for the other modalities, it's the same, but in this case, it would be an image, an object that's related to happy, but that doesn't have a language equivalent. Now, the interesting one is the middle one, is that there's cases that language, kitchen and oven together co-occur, and they also co-occur with happy. Problem is that three-way mutual information is, you could say, undefined, or there's a lot of hypotheses on how to compute it. The simple one will be just like three-way correlation where all of them are co-occurring, but there's a lot of downside on this, and one of them that I will give you at a high level is that sometimes when you mathematically look at it, it becomes negative. And this is why would it ever get negative? Like probabilities, like always positive usually, like if you think about it, but why would this become negative? This is like my kitchen and the oven and the happy. If I just look at it and count the number of occurrence of those three events, it should not like that probability, that joint probability should not be negative. But the way information is written, and for mutual information three-way, there's sometimes negative. And that's the whole thing about partial information decomposition, is that it's a numerical framework that allows us to study this. And I say it's an active research topic because even that is still evolving, but this seems to be the prominent one. That's why we presented it to you on Thursday, is that it seems that this value, which should be always positive, you're like, hey, kitchen and oven and happy should just always, but it seems to be sometimes it's negative. And the way they approach it mathematically is to say, let's factorize it. There's some positive factor and there's a negative factor. There's redundancy, which is the thing I talk about with the kitchen, and the word kitchen and the oven and happy. But once in a while, I tell you about the label, and suddenly my modalities get more connected. So I'm going to share that high-level intuition. I'm not going to go into math today, but the high-level intuition is that synergy happened because suddenly you have knowledge of the label, and your modality, when you know about the label, suddenly they get more connected. So an example would be in visual question answer. You have the image, a question. The image and the question may or may not be completely connected, but I give you the answer of the question, and suddenly the type of image you will imagine probably is only a subset of what it was originally. I give you more information, and suddenly that brought them closer to each other. We'll give you over the coming lectures a little bit more on this, but I want to give you the high-level intuition first. There's a lot of very interesting math. In fact, we're probably going to put one or two reading assignments around that. But that's what the main high level is, that we want to look at those co-occurrence of kitchen, oven, and happy. But sometimes knowing happy makes my connections between modalities closer. That's the high level of that. And that's suddenly that there's synergy. There's synergy because there's suddenly more interaction. That I know about the output suddenly brought my modality closer means that they are interacting. Those modalities are suddenly interacting in a way that connects them and the label closer to each other. If I didn't know about the label and I just observed the modalities by themselves, they were not as connected as suddenly there is a task that suddenly brought them together closer. And it brought them closer because most likely there was interaction between the modalities that predicted that label. And that's why we associate often synergy to this interaction, multimodal interaction. So I know it's a lot of information. I wanted to revisit that, and we'll continue to do that over the next few weeks. But what I want to emphasize, this is the high level between the input and output. We also talk about all those additive, multiplicative, and all these different type of internal mechanics. And what we'll talk about today is how do you align modalities. Now it's no more just a word and an object, but now I have an image with many objects, and I have a sentence or paragraph with many words, and how do I align them? That's the core of today's lecture. So the alignment is, at the core, is finding the connections. So alignment often is without the label, although you can also do it in a supervised way, but often the alignment is often just done from the modalities themselves, finding connections, finding those objects that relates to the words. And there are two types of alignments we are going to study. The discrete alignment, where both modalities have already been discretized. For example, an image has been discretized in a list of objects instead of being somewhat more continuous with pixels. Or even maybe speech has been discretized in either phonemes or words. And so there's already tokens for that. So most of the alignment is this way, but there's a nice upcoming line of research that says, hey, a lot of modalities are in fact very continuous. Like if I have those sensors from a robot, or I have even speech, like these are continuous signals, and alignment may not need to be discretized first. Maybe it should be aligned as two continuous signals. And then I will use these two types of alignments and revisit the problem of representation learning. But the representation learning we learned last week was about two elements. Now we'll have two ensemble of elements because you have an image with object and a sentence, and then we'll have contextualized representations. The landmark algorithm these days for that would be transformers, for example. So be happy. On Thursday, we talk about transformers. The whole Thursday is all about self-attention models and transformers. I will do my best to give you an intuition about them that goes beyond just those ugly figures you see and go a little bit more into the intuition of what is really a transformer doing, what is my hypothesis of what it's doing. So discrete alignment is the landmark, and that's where a lot of the research has been done. And we try to think of like ways of taxonomy a little bit, and that you could say alignment is on one side you do local alignment. What it means is deciding which object relates to which word, completely independent on all the other objects in the image. That will be a local decision. While global, you make your decision of alignment between object and words, you do it based on all of the object you observe and all of the words you observe. So there's a spectrum of local and global. And also we identify that sometimes the alignment is symmetric, like a word is related to an object, but sometimes it's directed. It's like that object is really related to that word, but maybe that word is related to many objects. So let's say, for example, people, like you have many people in the, and so it's like all of those people are related to that one word. So this more many to one, that's one example. Or it could be that just computationally, I decided to approximate this symmetric connection by a directed one. And I will give you an example, but a lot of the attention models were doing this in a directed way. So I will show you this as well. So the one that a lot of you who works maybe in multimodal will say, oh, alignment is the same as grounding. And the research community has started using the word grounding almost as a synonym of synchronizing or aligning modalities. I will say alignment was originally meant, and it was coming more from linguistic, is the idea of tying language, so it could be words or phrases or even sentences, is you're connecting, you're tying this to non-linguistic concept, like visual. Now, we started grounding audio with images or any other grounding. We're grounding everything with everything. I prefer the term alignment. You could say grounding it, but originally grounding was really about grounding the meaning of the words or the intent behind the words to the other modalities or other information or other contexts. So grounding was what it meant. And a step of it is aligning, which is for all the words trying to connect and find the alignment of which object it relates it or which series. So if you are to solve that, one very popular and powerful approach is to use what you've learned last week for this. And so if I have language and images and I want to link images and let's say I have supervised data on a small data set, I have training of paired data. What can I do? Oh, I gave the answer there. Coordinated representation. What this is I can learn representation of language and vision that are close to each other when I have positive pairs and far from each other without negative pairs. Contrastive learning is an example. Or the other type of coordination we talked about, where I learned these two embeddings in such a way that I coordinate. So I have paired data and I make this coordination function is the idea in a sense of just taking positive example. And I'm just, for those positive example, optimizing a loss function that brings these as slow. So we talk about the extreme version, which is just cosine similarity, which you mostly force these two as being almost the same when they are paired example. But there you will need paired data. That means you have data where you already annotated words and their related objects. And as we discussed earlier, just a second ago, we said there's another approach that also add the negative example in it through the contrastive learning. And as we discussed even just today, this is really focusing on that common shared information, that co-occurrence. So you're saying if they co-occur meaning there is paired data with it, then that tells me that they're close to each other. That tells me that their embedding should be also close to each other, and that's the loss function. So that's a very popular approach to do alignment, learning those coordinated. But I'm also going to give other approaches. In fact, the birth of transformers comes from this idea of attention. So who is the parents and the grandparents of transformers? So the parents of transformers are these attention models, which I will discuss. And the parents of that parent is just a gated models, any kind of gating, because attention is just a gate. So I will show you an example of that, but the beautiful thing of gating is that dynamically, I'm going to change the weight of my model. Before that, most model will be trained with a bunch of weights that you are optimizing during training. You're optimizing your model parameters during training, but at test time, those model parameters stay the same. They are the same, these model parameters. The idea of gating is that suddenly I'm going to have dynamic parameters that are changing at test time, at inference time, that will change based on whatever I observe. The observation of that sample will change my weights. My weights are dynamic. I'm gating in the sense that I'm dynamically opening or closing a gate. Opening and closing a gate is just multiplying by a dynamic weight. Now, so that's the grandparent. The parent is just renaming it gating with attention model. So attention is just a rebranding of their grandparents. So is now I'm going to take this idea of dynamic weights, but I'm going to use that in a specific kind of framework where the intuition of attending, if I attend to something, a simple way to attend to, let's say I have 5 features and I want to decide which feature to attend to. I can dynamically decide which of the feature to attend to. I will multiply each feature by a weight that will decide if I should or not keep that feature. If that weight is normalized, if those weights are normalized, then I can call them attentions because I'm attending, I'm normalizing on my weight, I'm deciding which one to attend to. So attention is a nice normalization of the gait, or even gating was sometimes normalized. So here I will say, I heard some description of the image. So it's going to be a directed alignment here that I'm going to do. And what it is, I have a modality language that's a caption, and I will try to see what are the objects that are related to that query, to that words. You can do it the other way around. You can direct the other way. So I have an objects in the image, and I have a nice image. And so here I have the word frisbee, and I ask myself, which of the objects is related to that? I'm trying to align that word. I'm in fact going to try to align all words to all objects. So with this, one way to do it is to take the image and detect all the objects. But there was a cool thing with the CNN, and I will show you in a second. But the idea is that I'm going to attend, for this object, I'm going to attend to only, for this word, I'm only going to attend to certain objects. And the soft attention, which is the parent of the transformers, is saying, okay, you have all these possible candidates, and I'm going to predefine a grid over my image, or it could have been just a list of objects. But when attentions were first introduced, it was a grid. And so I will say, I'm going to it's going to be a weight, a dynamic weight for each of those grid. Each of those grid, I will have a weight and attention to it. So in this case, the CNN was really cool, and I'm just going to give quickly, is that instead of taking the last layer of the CNN, which is the fully connected, what's really nice in this is, in fact, to use the layer before the convolution. If you remember, I have a 640 by 640, 320 by 320, 160 by 160. At some point, it's a smaller image that represents the big one. That is a really good place, because there I can create a grid of 8 by 8 or 4 by 4 and say which part of the image is related to my word. So what I will get is, I go ahead, this is for image captioning in this case. So I get the image, and then I'm like, okay, let me look at all the objects and let me predict one first word. That one will be kind of a little bit arbitrary. And then I select that word, that first word that I predicted, and now giving that word, I will look at what are the section of the image that are relevant to that word. But to know which one it is, these attention weights are going to be computed. So what it is I have a first word, let's say the frisbee. And now I'm going to decide where in the image to look. And for that, I'm going to detect which objects are related to that word. And that's the attention, that's the dynamic weight that you're computing. And that will tell me which object to look at. And then I will study this subset of objects, and then from that predict the next word. So let me give a restating of that. The key aspect is here. One option would be to always give all the objects to predict the next word. That will be the simple thing. That's the way things were done. The idea is that every object are used to generate every word. But in reality, only a subset of our objects are likely to be used for the next prediction. And it's easier, I just realized I removed that slide. It's easier to do it for machine translation. Le chien sur la plage. What is it in English? Yeah, the dog on the beach. Thank you. And I only know 2 languages, so I'm not going to do it in other languages. But for translation of one word, a sentence to another sentence, this is even clearer there, because to translate the dog on the beach, I don't need to know, in fact, beach to translate the dog. The dog in itself is sufficient to, so from all the sentence, I don't need to know all the words in the sentence. If I could be a very, very long sentence with many verb phrases, I don't need to know. Only a subset of it is relevant to my current translation. That's the idea that I'm translating one word at a time. And that's the idea of attention. The attention, and that's why it's the parent to the transformer. And I'm going to go, I'm here, I'm giving attention at a high level. On Thursday, I'm going to go very deep into the math, but also the basic idea is that for every prediction I'm making, there's only a small context that's important, that's relevant. And the idea of attention is the idea of automatically deciding what is the relevant context. And that's what the transformers does so well, is contextualizing each word with all other words for bird, and we'll discuss that more in details. But in this case, I'm trying to create predict the words that describe the image, but when I make those predictions, I don't need all the objects at every moment I'm predicting words, because le chien sur la plage, only a subset of that. Now you could ask yourself, why don't I do always each word one and just translate each word? But for example, in French, the greenhouse will be said as the house green. Okay, that the ordering of adjectives, and you've probably also for all the languages, you know probably a lot more than me. There's a lot of those. So that's why the context is not just one word, it's a few words. The same way, it may not just be one object, it may be a few objects that helps me predict that. So that's the important aspect. And so the attention mathematically is that as I'm predicting the next word, I will take into consideration the previous embedding, but also a subset of that. So Z is the previous embedding of the image. That's just because I'm predicting in a recursive way. But the important part is this S, which is the current, like what part of the image is useful for my current prediction. That one, that is as in the before was I'm going to use the whole image the whole time. Now I'm going to customize it every time, and it's going to be customized by simply, it's a weighted average. I'm going to, from all of the objects, I'm going to decide dynamically as I'm predicting every word. I'm going to decide on a subset of the image to decide which one are relevant. These attention weights are decided dynamically, and the way they're decided is a neural network, is a 1, 2, 3 layers neural network that will take maybe the input or take the previous state, and will decide where should I focus next. In the language, le chien sur la plage, I did the prediction of the dog. Then there's kind of an implicit thing that because I've done the dog, then I'm really likely to go to the next word. So that's one of the easy one. But if I start seeing don't even speak French anymore, la maison verte, and I translated as the green, but the green, I still need to use all 3 words, la maison verte, all 3 of them. And so my prediction of the green tells me what other word I should be looking at. So that's the intuition for the attention. I wanted to give, and the attention will usually be normalized. And that's why I said it's gating, that's the grandfather, but it's normalizing, it's deciding, it's a soft max usually. on this is a simple normalization on this. And so, and this is just the learning parameters. But at the end of the day, you are looking at all the image, and then in fact, you're not deciding which pixel to use, but which embedding of the pixels is just a small difference that you have. And that's really nice because now you get a nice mapping. A woman is throwing frisbee in the park. So it's a nice one-to-one mapping between objects and that. And that was 2015, which is almost 8 years ago. And a year before, it was a machine translation paper that looked at attention models. And I want to point out quickly, I don't want to discuss as much. It's not as popular these days, although with RL being more and more popular, you see some extension of that. But it's a soft attention. I have a weight for every object. But what if I decided that there's only one object at the time that's relevant to my prediction? It's a decision. It's called a hard attention. I will not allow a soft attention. I will say, no, there's only one object. And optimizing that can be, I mean, this is a recurrent, we don't use recurrent neural network as much these days, but a recurrent neural network version. But the general idea was, I'm going to store a location. So it's not a weight, but it's a location in the image, and I'm going to update that location as I'm making prediction. I make prediction of words, but I'm changing my location. The interesting one is the next one. And you may hear about optimal transport. I'm going to give you at least an intuition on these kind. It's the idea that it's not that I'm aligning one word at a time to the image. Is now I'm going to align all the words and all of the objects together at the same time in a global way. And that is very interesting. So this can be done because maybe I gave you a caption and an image, but I didn't tell you which object is related to which word. I just gave you the sentence and the image. So it's a kind of a weak supervision. I know that they're related, but I don't know which object and which word are related. So for that, I will need to do two things to learn. So if I want to learn a representation for image and caption, all of the previous theories and math and all this we've done was I've already given you a word aligned with objects. That's easier. But here I gave you a weak supervision where I only give you the all of the sentence and the object. So there, you're going to need to learn a representation of language and vision. You're going to need to do two things. First, you're going to need to learn a representation. Learn a representation for language and vision that are close to each other. But you also need, as a latent part of your optimization, you're going to need to see what is the best way of aligning words with object. So your loss you probably will have two terms. Yes, you're trying to get them as close as to each other, but also you need to take into consideration that alignment between words and objects. So how do you do this? And I will give you 2 slides of probably a full course on that topic. Very interesting work, but the idea is I'm going to show a simple version that mathematically is easy to understand, and then I'm going to give you an intuition of the more complex version that is probably the one you will use if you use it for alignment. But the simple one is, I will make some assumption. I will say, suppose that each word can only be connected to one object. And suppose that every word is connected to one object. So it's a big assumption, because same number, and I have the same number of objects and words. Okay? So it's a lot of assumption. So, and there's all elements are assigned, which means that for now that they're all assigned to at least one object. So it's a very hard case. And there, in this case, I will say that there is this function that goes from one modality, let's say words, to the other modality, let's say object. This is the really interesting one that assign words and object, and that will be based on a weighting. The weighting is this idea that an object and a word are close to each other if their embedding is close to each other. That's usually how it is. So each of these links will have a weight associated. I only showed you the solution, but the optimization will be fully connected. Every word will be fully connected with every object, and they each have a weight associated with it. The weight is that embedding, and the goal is to find those links, this solution, which has the highest weights, that where the closest words and images. So I have all that optimization I want this to be as close to possible. Now, suppose for a second that it's not a two-part optimization. Suppose I already pre-trained my clip embeddings. Okay? If it is done, then this optimization is quite, you can imagine what it's doing now. So I already trained a clip embedding, let's say, and I will just optimize which words are connected with which objects. And how do I do it? Is because there's a clip embedding for words and a clip embedding for objects. And then my algorithm is going to automatically find the highest weight that gives me an assignment for every word and every object. That's if clip was already trained. And the interesting part is going to be that I will have both of them optimized. And the simple way to do it is the chicken and an egg. It's like you fix one, you optimize the other, fix the other, you optimize. There's different ways to do it, but the simple way will be to just alternate the optimization between alignment and representation learning. So to do this, the naive way is to check all possible assignments. You check all possible assignments. So that means you have fully connected and you say, I'm going to try, okay, let's say I take this word with this object and I tried one version and I see the weights for it. But the reality is that there is ways that have been established in linear programming where what you will do is you start transferring this formalization into a linear programming where in this case you have, if you have a pair that's active with a certain weight, and then you are going to optimize through linear programming, and there's very well established algorithm like the simplex algorithm that will take this formalism and find the optimal weights for you. That's 2 lines. You can do it in Python. It's very simple to do. Now, the one last thing I will discuss, and probably that's the last one I will do for today, is that you can go a step further and now don't have all those assumptions. The assumption will be a lot smoother, a lot more flexible. And there you will say you have a different number of elements, so you will allow the number of elements to be different, and you will allow a many-to-many, a kind of a soft assignment in a sense of all of it. So that's a little bit closer to attention. That's a little bit closer than You could say almost to transformer, but yeah. So the many-to-many self-assignment, and the reason it's called optimal transport is that one intuition is that you have one modality. Let's say you have 5 features in that modality, okay? And then let's say you have, in a sense, you could imagine almost a probability over those 5 features. You're transporting it to another modality that maybe have 10 features, and again has probability over it. So you're moving Earth from one landscape over 5 features to another landscape over 10 features. You're transporting, you're moving Earth. That's the intuition. You're transporting element from one modality to another. You're transporting your density function, in a sense, from one modality to another. And so in this case, the alignment will allow for any word to be connected to any object, like the previous one. So the previous one, we had a weight for every word and every object, but the solution could only be one word, one object. Here, the solution can be for each word many objects, and for each object many words. And the weight will be the same as before. So you could imagine you already got clip embedding, and then the maximize is very similar as the previous one. And you've probably heard about Wasserstein distance. This is one way you can optimize that. I will not go into the math of that for this time, but there's nice ways of optimizing that system of equation in a way that you get a solution that gives you these weights, these optimal weights. So what we'll do on Thursday will be the continuous alignment. I will, instead of rushing it, I will do it on Thursday. And we'll also discuss on Thursday the transformer as well, or at least start that with including BERT. Okay, thank you very much.